Good morning, guys. How is your holiday? I hope you enjoy it, even though you still have to stay at home. Even though you cannot go anywhere during the holiday, but at least you can just enjoy your free time. You don't have to be busy with any assignments. So now I hope you're ready for a new day. You are refreshed and prepared to have some more lesson and also some more assignment, of course. Today we will discuss question paper 32 from summer 2012 exam. Let's begin. The first question is about light. This is question number 4 from the paper. Figures 4.1 and 4.2 show a semicircular glass block as rays of blue light are directed into the block at different angles. The rays are directed towards the center C of the semicircle, so that no refraction occurs as the rays enter the block. 4a. At the angle shown in figure 4.1, no refracted ray emerges from the block at C. 4ai. Determine the angle of reflection at C. To determine the angle of reflection, first we have to draw normal at point C. This is the normal. The normal must form a 90 degrees angle to the surface of the glass block at point C. The angle of reflection is formed by the reflected ray and the normal, and the angle of reflection is represented by letter R. To know the angle of reflection, we have to know the angle of incidence. This is the angle of incidence. The angle of incidence formed by incident ray and normal. Remember, this is a 90 degrees angle. So if that angle equals to 40 degrees, then the angle of incidence, or I, equals to 90 degrees minus 40 degrees. This equals to 50 degrees. Remember, angle of reflection, or R, always equals to angle of incidence, I. So, in this case, I equals to 50. Then R also equals to 50 degrees. So that's the answer for question 4AI, 50 degrees. Question 4AI. State the type of reflection occurring at C. This type of reflection is called total internal reflection. Question 4b. Calculate the refractive index of the glass. To calculate the refractive index of the glass, we have to analyze the condition of the refraction. Some of the ray emerges in air close to glass surface, and some of the ray reflected. Now draw the normal, pass through point C, and form an angle of 90 degrees to the glass surface at point C. From this drawing, we know that the refracted ray form a 90 degrees angle to the normal. Or we can say that the angle of refraction, this angle, which is formed by the refracted ray and the normal, equals to 90 degrees. If the angle of refraction equals to 90 degrees, then the angle of incidence, this one, is the critical angle. Once again, if the angle of refraction is 90 degrees, then the angle of incidence is the critical angle. The angle of incidence formed by the incident ray and normal. The equation involving angle of incidence, which is the critical angle, and the refractive index of the glass is this one. Sine of IC is the critical angle, equals to 1 over n. N is the refractive index of the glass. To know IC, look at this angle. This is a 90 degrees angle. So, if that angle equals to 50 degrees, then the IC, or the critical angle, equals to 90 degrees minus 50 degrees, or 40 degrees. So, sine of 40 degrees equals to 1 over n. This gives us n equals to 1 over sine of 40 degrees. 1 over 40 degrees equals to 1.56. This is a round-off number. So, the refractive index of the glass equals to 1.56. Refractive index has no unit, so you don't have to write anything behind the value. Let's continue to question 4C. The experiment in B is now repeated with red light. On figure 4.3, draw and label the paths of the reflected and refracted rays of red light. The dashed lines show the paths taken by the blue light in B. Remember, reflection does not affected by the refractive index of the medium. Since the incident ray of the red light takes the same path as the incident ray of the blue light, then the reflected ray of the red light will also take the same path as the reflected ray of the blue light. So for the reflection of the red light, we will get this path, exactly the same as the path taken by the blue light. For the refraction, we have to consider the refractive index of the medium and also the wavelength of the light. We know that the incident ray comes from the glass block into the air. Glass block has higher refractive index than air, so the light will be bent away from normal. Let's draw the normal, passes through point C, and forms 90 degrees angle to the surface of the glass block. The path taken by the blue light is this one. The path taken by the red light after the refraction will be slightly above the blue light. Why? Because red light has longer wavelength than the blue light. The longer the wavelength, the closer the light will be bent from its original path. Or in other words, we can say that the shorter the wavelength, the farther the light will be bent from its original path. The original path of the red light is this one. So, the refracted ray of the red light must be drawn slightly above the blue light. Once again, Because the blue light has shorter wavelength, it will be bent farther than the red light. So this is the path of the red light. Let's discuss number 4D. Figure 4.4 shows a 45 degrees, 90 degrees prism used in an optical instrument. Part of the path of a ray of light passing through the instrument is also shown. Light leaves the instrument along path B. In the dashed box, draw another 45 degrees, 90 degrees prism and complete the path of the light through this box. Look at the first prism. This is a 45 degrees, 90 degrees prism. Usually, when a ray of light passes through two different medium, the light will be refracted. The light comes from the air into the glass prism. So, it's supposed to be refracted closer to normal, since the glass prism has larger refractive index than the air. But, in this case, the angle of incidence equals to 0 because the ray of light align with the normal. When the angle of incidence equals to 0, the refraction does not occur. Therefore, the light will pass through the air and the glass prism as a straight line. There is no bending of the ray of light here. Then, when the ray of light strikes the hypotenuse side of the prism, total internal reflection occurs. So, the light will be reflected to the other side of the prism. Then, the same thing happens as before. The angle of incidence equals to 0, which makes the light passes through the prism and the air as a straight line. Remember, this event only happens inside a 45 degrees, 90 degrees prism. The light must leave the instrument along path B. So let's make the path that the light must take to leave the instrument along path B. This is the path. Now, let's draw another 45 degrees, 90 degrees prism inside the dashed box. Remember, the light only passes through two different medium as a straight line if the angle of incidence equals to 0. So, we have to put the right angle sides at the top and the right side of the dashed box, like this. Then the light will be able to pass through the path that we have drawn. Number 5. Figure 5.1 shows a view from above of waves on the surface of water in a water tank. The wavefront AB is traveling in region P towards region Q, where the water is yellower and the waves travel more slowly. Question A. Sometime later, the wavefront has moved into region Q. CD, CE, and CF are suggested positions of the new wavefront. AI, State which is the correct position of the new wavefront. To find the correct position of the new wavefront, we have to go back to the previous slide. Draw the direction of propagation or motion of the wave. This is the direction of propagation. The direction of propagation must be perpendicular to the wavefront. So, this has to be a right angle. At the position where the direction of propagation meets the boundary between two regions, this position, draw a normal. The normal must be perpendicular to the boundary. Because the waves travel more slowly when they enter shallower region, the direction of propagation will be bent closer to normal. Draw the prediction of the direction of propagation in region Q. The direction of propagation bent closer to normal. Then, from the drawing, we can see that the most possible position of the new wavefront is CD, because CD form a right angle or 90 degrees angle against the direction of propagation. Let's put our answer on the provided space. This is the answer for number AI, CD. I. Explain your answer to I. The wavefront changes direction or refracted as it enters the shallower water. In Q, the wavefront will be bent closer to normal as it has shorter wavelength. So, B will become the center point for the wave to spread in Q. Let's continue to question 5B. Figure 5.2 shows the waves after a change is made to the way the tank is set up, and the experiment is repeated. The wave from position AB in region P now moves to position CG in region Q. State the change that has been made and explain your reasoning. The change that has been made is regions P and Q now have the same depth. The explanation for this change is the wavefront does not bend when it enters region Q from P.